Hello, George Notchik here. This is the beginning of a series of lectures that's aimed to develop the viewer's skill in understanding the methods of applying the mathematical disciplines of plane geometry in trigonometry to model the geometry on a sphere. In future modules, I will set up and derive formulas and equations related to curvature on a sphere, the drop distance from a tangent touching the sphere down to its surface, angular measures, perspective, features of objects hidden beyond the horizon line as a function of viewer height, how to triangulate the distances to objects in the viewer's far field and in the sky, parallax methods, the Earth's bulge between a viewer and an object, and if time permits, we will discuss vectors as related to velocity and acceleration and discuss some celestial mechanics. I will introduce some celestial mechanics along the way, some simple items as we progress. The requirements in these videos is going to be rather minimum. I'm not expecting the user, the viewer, to have an in-depth understanding of algebra, just some basic algebra. I'll introduce and fill in the gaps along the way on certain concepts. Most of the videos coming up are going to be timed so that they're no longer than 20 to 30 minutes in length. The exception is this particular lesson 1, which is going to be about an hour long because I have a lot of definitions to go through and a lot of concepts in teaching you the language of geometry. In the future, what we'll do is probably around module lesson 4, we'll start talking about trigonometry. That will take up 1 or 2 lessons, and then after that, combining that with what we're learning in the first few lessons about geometry, we'll be able to start working with geometry on a sphere and start deriving a lot of these equations and formulas that you find in like the Metabunk calculator and other calculators online. I'll show you where these equations come from and how to easily derive them. So, we'll get started here now. After completing these series of videos, you should become fairly proficient in applying the methods of trigonometry and geometry in solving a variety of problems. There are 3 main branches in geometry. There's plane geometry, which has to do with two-dimensional figures, figures that can be drawn like on a flat surface such as a piece of paper. These are closed figures like rectangles, triangles, circles. And then there is solid geometry, which has to do with three-dimensional solids, things like prisms, cubes, tetrahedrons, spheres. And there is analytic geometry, which makes use of coordinate systems along with algebra to solve problems in geometry. We are going to focus on plane geometry. It's been around for over 2,000 years. The Greeks were masterful geometers. Euclid published a book called The Elements over 2,000 years ago, which was probably the first comprehensive math text. Fortunately, much of what we will be doing with spherical geometry can be solved with plane geometry because of the perfect symmetry of a sphere. You do not need to use three-dimensional coordinates and three-dimensional 3D solid geometry to solve many problems on the sphere. The reason is, for example, suppose you're on the surface of a sphere and you're viewing an object in the distance, say maybe like a tree, and you want to determine the height of the tree or some other issues related to this problem. Well, rather than having to set up three-dimensional coordinates, all we have to do is pass a plane between the observer and its target that it's trying to determine, heights or whatever. And if you say take a plane, pass it through the center of the sphere, and then tilt it up to include these objects, then you can do all your manipulations and perform your mathematics on the plane. You don't have to worry about anything outside the plane because of the symmetry of a sphere. It allows us to do this sort of thing, so we can use plane geometry to solve many of these problems on a sphere. Mathematical methods use very precise language with no ambiguity, and that leads to the success in modeling real-world problems and reality itself using mathematics. Mathematical modeling gives us insight into the nature of the problem at hand and answers to questions we may have regarding the system modeled with the mathematics. With a good mathematical model, we can even make predictions as to how the system will behave as we change inputs and various parameters within the system. Its usefulness comes in, say you have a system and you can do non-destructive testing with the system mathematically. And it will also tell you how the system will behave to influences that might be too expensive to incorporate in the laboratory on a prototype, or just might be too dangerous to perform. Okay, now in order to communicate effectively in mathematics, we have to understand the language of mathematics. For example, engineering terms of level and flat are often misunderstood by the non-engineer, which leads to a lot of unnecessary arguments and misunderstanding. Flat in these disciplines means something that is a plane, like a sheet of plywood or wallboard, something very, very flat, which is independent of gravitational influences. Level, however, means something that lies along a gravitational equipotential and assumes a state of minimum potential energy. Water with a flat surface is not necessarily the same as water that is level. These words are used interchangeably in the lay world of everyday usage, but to engineers, surveyors, and physicists, they have totally different meanings. They're not interchangeable. For example, suppose we have, say, the surface of the Earth. Now, if there's, say, water resting on the surface of the Earth, then we call this level. That is, every point on the surface of the sphere that the water is resting on is equidistant from the center of mass. So everywhere along a surface that's equidistant from the center of the Earth is at the same gravitational potential, and the potential energy of the water anywhere along here has the same value. So it's reached a minimum potential energy. It won't move. This is what we call level. Whereas flat would be, say we had a gigantic sheet of wallboard or plywood and we just laid it so it touched the surface of the sphere or the surface of the Earth at one point. Well, if we did that, then if you went out far enough from where it touched the surface of the Earth, there will be a gap. And that gap will get wider and wider as the further you go out. the green is level, whereas the contour that follows the sphere, the surface of the sphere, is what we call level. So level is not flat in this usage in the case of dealing with spherical masses. So language is very important in mathematics, as this example shows, so that there isn't any ambiguity by what we mean by when we use certain terms in mathematics. Now, what I'll do is I'll begin defining terms we will use in geometry and introduce more as we proceed along in these various modules. And as we need these terms and definitions, I will introduce them. But first we need to get started with some fundamental definitions and terms related to geometry. Our first term is polygon. A polygon, as the name implies, poly meaning many, a polygon is a figure, a closed figure of many sides. For example, under the class of polygons we have triangles. Tri meaning three, or a three-sided figure is a triangle. And then we have a four-sided figure we call rectangle. And five-sided figure is called a pentagon, penta as in five, hexagon for six, and so on. There's a number of terms used to describe closed figures with multiple sides, but we aren't going to go into these higher order figures. We won't need to. At most we'll be dealing with triangles and rectangles. Now, the triangle is very basic and very important because we can usually, once we know the properties of triangles, we can extend it up to higher order figures. For example, if you have a hexagon, which is a six-sided figure, you can break it up into triangles. So we have 6 triangles in a hexagon, so we can do our geometry in each one of these little triangles and use that to describe the overall nature of the hexagon. And for example, on a same thing with a rectangle, you can draw a diagonal and you have 2 triangles that you can deal with. And you can do this with any number of polygons. Is you can always break it up into several triangles. Now, the thing is, we have interior angles, angles that are in the inside, and the number of interior angles is equal to the number of sides. Like with a triangle, you have 3 sides, you have 3 interior angles. With a rectangle, you have 4 angles, and with the hexagon, you have 1, 2, 3, 4, 5, 6. 6 sides, 6 interior angles. So you have as many angles as you have number of sides. Now, there's a term that we use. It's called congruency. Congruency means the same. That is, 2 figures that have the same size and the same shape are called congruent. They're exactly the same. Now, the symbol we use for congruency is an equal sign with a squiggle on top. That's what we mean by things are congruent. That they have the same size and shape in all respects. Then there is similarity, or similar. And we just use a squiggly line to say similar. Things that are similar have the same shape, but not necessarily the same size. Congruency is a lot stronger. Things that are congruent are also similar, but things that are similar are not necessarily congruent, because in similarity we have the same shape, but not necessarily the same size. But with congruency, it's both the same size and the same shape. Now, in plane geometry, we'll be dealing with straight lines, and we'll be dealing with arcs. We have lines and arcs. And then we also need to understand the concept of parallel lines. We indicate parallel lines in this fashion when we're writing it out in text. We just put two parallel lines next to one another. But parallel lines go on forever in each direction, and they never intersect. They never cross over on one another. That's what we mean by parallel lines. Now, lines go infinitely in both directions, and there's an infinite number of points on the line. This is our definition of a line. It just goes on forever in both directions. Now we have another object that we call a ray. A ray starts at a specific point and goes out infinitely outward from that point. And this is called a ray. You can think of it as being a half line. A line, if you pick any point on a line, then there'd be two rays, one going outward to the right, one going outward to the left, in this fashion. Arcs that we will be considering will be those sets of points equidistant from a fixed point, as in segments of a circle. Say we have a circle. A circle is defined as a set of points that are equidistant from a fixed point, which we call the center of a circle. And a line segment, or an arc, not a line segment, but an arc, would be just a portion of that circle. That is an arc. This would be an arc. This is a much larger arc. But arcs will be segments on the perimeter, on the outlying perimeter of the circle. Now, the circle, as you know, is a closed plane figure whose locus, or set of points, is a fixed distance from the center point, which we call the circle's center. The distance from the center to the locus of points is called the radius of the circle. We'll designate that with a small letter r. The radius of the circle is that distance from the center to the perimeter. The outside locus of the circle is called its perimeter. Now, a chord, C-H-O-R-D, is a line segment that connects 2 points on the circle. Chords can have different lengths. That is a chord. This is a chord. This is a chord. Chords connect 2 points on a circle. For example, that would be a chord there. Now, the chord that passes through the center of the circle is given a special name. We call it the circle's diameter. So a chord that connects 2 points on the circle, perimeter of the circle, that passes through the center is called the diameter. The diameter has a length twice the radius. From the center out to that point on the chord is r. From the center out to this point on the chord is also r. So the overall length of the diameter is 2r. Now, for any circle, no matter how big or small, the length around the perimeter of the circle is called its circumference. So if we have the circle, if we start at a point and take a tape measure, go all the way around the circle, that length we call the circumference. And I'll designate it with the letter C. Now it turns out that a property of circles that holds for any circle, no matter how big or how small, that the ratio of the circumference to the diameter is equal always to a constant, which we call pi, and designated by the Greek symbol pi. This holds for any size circle, no matter how large or how small. If you take and measure the circumference around the circle and then divide by the diameter of the circle, you always get pi. Now, we can see that circumference is equal to pi times the diameter, and since the diameter is 2 radiuses, or radii, we can call it 2 pi r, since the diameter is 2 radii. So the circumference around the circle is 2 pi r. Pi is a constant. It's an irrational number, which means it cannot be represented by the ratio of 2 integers. It's a non-repeating decimal. It goes on and on forever. Pi has a value of
3.141526535979323846
64333833279. That's the 30 decimal places. Now, we don't need to have that kind of accuracy for pi, but there are 2 approximations to pi that are very useful. Pi is approximately equal to 22/7. 22/7 is 3.14286. So this is high. You can see that it's larger in the 3rd decimal place than the actual value for pi. This is high by 0.0402%. So roughly 4/100% high when you use 22/7. Now, another good approximation for pi, which is much better, is 355 divided by 113. And this value is 3.141592920. So you can see that that's 9. So comparing, the digits are good 2, 4 to the 6th decimal place. And this value of pi, if you look, after the 2 we have a 9. In the actual value of pi it's 6, so this is also high, but this is high by 84.9 parts per billion. So it's really quite accurate. I mean, it's good to 6 decimal places. So these 2 approximations I'll be using in these discussions as we proceed ahead. Now, pi could be considered the most fundamental mathematical constant pertaining to geometry. It shows up all the time because it is the ratio of a circle's circumference to its diameter. Another constant, E, shows up a lot in math and physics, or engineering and physics, and its value is 2.71828182846. You can see that it repeats there at the beginning, but after that it does not repeat. There's no repeating decimals in E either. It's an irrational number. And this shows up a lot in engineering and science because it appears a lot in changes involving natural processes. But we won't be using E, we'll be using pi. Now, we'll start talking more about definitions in geometry, geometrical definitions. An angle is defined by two rays originating from the same point, which we call the vertex. So we have two rays emanating from the same point, and that defines an angle. The rays define the sides of the angle. We have two sides to the angle, and these are the rays. And we designate angles by drawing an arc between the two sides. Now, angular measure is established by first designating a reference line. So if we have a reference line and we pick a point and we start with our ray and we sweep it, then the so-called distance that is between the two sides defines the angular measure of the angle. Now, if we sweep it in a counterclockwise direction, this is the positive direction for angular measures. So angular measure sweeping counterclockwise are positive angles. Angles that start from the reference and sweep clockwise are negative measure angles. So we could say sweep up here. This looks like it might be about a positive 45 degrees. Sweeping down this way, it would be a minus 45 degrees. So sweeping from the reference counterclockwise establishes a positive measure for the angle, and going counterclockwise gives you a negative measure for the angle. Now, we define angles on a circle is the best way to look at it. So if we start with a circle and establish a reference which goes through the center of the circle, this is our reference line, and we sweep a ray up starting from the reference, say going in a counterclockwise direction, we can call this angle A. A lot of times we use letters to designate angles or numerals. Now, one rotation around the circle is taken as an angular measure of 360 degrees. So one rotation is 360 degrees. Fractional parts of the rotation gives a smaller angular measure. For example, if we say start at the reference and go halfway around the circle, then the angular measure is half of 360 degrees or 180 degrees. If we go, say, a quarter way around, then we have an angular measure here of 90 degrees. And any smaller amounts of rotation are taken as a fraction of the full rotation around of 360 degrees by the amount of the fraction that we go around the circle. So our angular measure is determined by how far around the circle we go. Now, there's very specific names that we give angles. If we go a quarter of the way around the circle, we have an angle of 90 degrees, and we call this a right angle. And we designate right angles by putting a little box or a little rectangle at its vertex. This is called a right angle. A right angle is 90 degrees. An angle that goes halfway around is called a straight angle. That's 180 degrees. And if we make a complete revolution around the circle, we have what is called a full rotation, which is 360 degrees. Now, there's other special angles, is if we say have a circle and if our angle lies between 0 and 90 degrees, we call this an acute angle. So angle A is an acute angle. If the angle lies between 180 degrees and 90 degrees, such as angle B here, we call this an obtuse angle. And if the angle is greater than 180 degrees, such as if we take an angular measure, say, going from here to here, this would be angle C. This is a reflex angle. Okay, these are terms that we'll be using. Now, if we have two angles in that sum, say we have angle A and we add to it angle B, and if that sum is 90 degrees, we call A and B complementary angles. And if the sum of two angles is 180 degrees, we call them supplementary angles. Very important terms. Complementary angles sum to 90 degrees. Supplementary angles sum to 180 degrees. So, for example, let's say we have a right angle and we have two angles. This would be A, or this, say this is angle B, and this is angle A. Well, angle B plus angle A sum to 90 degrees. So A and B are complementary. And if we have, say, two angles, say this is angle A, and this is angle B, A plus B is a straight angle, or 180 degrees, or sum to 180 degrees. A straight line has an angular measure starting from one point and sweeping over to another point of 180 degrees, which is called a straight angle. Now, so in this case, A plus B is 180 degrees. In this case, A plus B is 90 degrees. So we have complementary angles, supplementary angles. Now, we just said that the angular measure going around the circle in one complete revolution is 360 degrees. Now, there is another unit of measure for angular measure, and it's called the radian, which is very important. Now, a radian in angular measure is defined as an angle A has a measure of 1 radian if that angle subtends an arc on the perimeter of the circle of length equal to the radius. So, if I take a circle and I take its radius, say take a piece of string and then lay it on the perimeter of the circle so that the arc length on the circle perimeter is, that total length is r, then that angle whose sides go through the endpoints of that radius, we say that this angle subtends that arc, then this angle A has a measure of 1 radian. Now, since the angular measure is related to the arc length on the perimeter of the circle and we can take, since the perimeter or the circumference of the circle is 2 pi times the radius, we know that. Well, that tells us how many radiuses will lay along the perimeter of the circle. Exactly 2 pi radii. If we were to put them end to end, say take and lay out another radii, and then another radii, and so on, all the way around, we would find that there will be 2 pi of these radii that fits along the perimeter of the circle. So there would be 2 pi radians in the circle, because each radii defines a radian measure on the angle of 1 radian. 2 pi is roughly 6.28. So that tells us that there's about 2.8 or 6.28 radii that will lie along the circumference of the circle. Now, since a complete revolution around the circle is 360 degrees, we can get a relationship between the degree measure and radian measure. 360 degrees is equal to 2 pi radians. Or dividing through by 2, we have 180 degrees in pi radians. Well, how much is 1 radian in terms of degrees? Well, if 1 radian, if there are pi radians in 180 degrees, then there will be 180 divided by pi degrees in 1 radian. Well, pi is very close to 3, so this would be approximately to 180 divided by 3. Pi is a little bit greater than 3. 180 divided by 3 is 60. So 1 radian is a little bit smaller than 60 degrees. A radian is actually 57.296 degrees. So it's about 0.73 degrees, or 3.7 degrees, or 2.7 degrees less than 60 degrees. So 1 radian is almost 60 degrees. Now suppose we want to convert between radians and degrees. By knowing this relationship, that there are pi radians in 180 degrees, it's a very simple matter to convert between one and the other. Suppose we have an angle of 5 radians. How many degrees is that? Well, we know that there are 180 degrees in pi radians. So we multiply by 180 over pi to get the degree measure. So we have 5 times 180 divided by pi, which is 5 times, remember 180 divided by pi radians is 57, say 0.3. So this comes out to 286.5 degrees in 5 radians. How about going the other way? Suppose we have 120 degrees. How many radians is that? Well, we flip this around. Since we have 120 degrees, we divide by 180 degrees and multiply by pi radians. So 120 over 180 is 2/3 pi radians. Now, when we're dealing with radian measure, rather than multiplying and dividing out this by substituting 3.14159, so on for pi. We leave it in this form when we're dealing with radian measure. That's usually the accepted convention, is always express radian measures if pi is involved by just putting pi there rather than substituting the decimal equivalent for pi. So there are special angles that you should commit to memory. 90 degrees is pi over 2 radians. Remember, there are 2 pi radians in the circle. 90 degrees is 1/4 around the circle, so we divide by 4, so this is pi over 2. 90 degrees is pi over 2 radians. 45 degrees is half that, or pi over 4 radians. 30 degrees is pi over 6 radians. 60 degrees is 2 thirds, or pi radians over 3. Okay, it's twice 30, so it's pi over 3 radians. 180 degrees is pi radians. A lot of times I just use RAD, I abbreviate radians. And 360 degrees is 2 pi radians. So these are the special angles that you should know between degrees and radians. 90 is pi over 2 radians, 45 is pi over 4, 60 is pi over 3, 30 is pi over 6, and so on. Now, when we're dealing with angles, we use a notation for expressing angular measure. There's a number of different conventions. There's 2 that I'll use on and off. Is to designate angle A, we kind of draw an angle and we put an arc in there and we call that angle A. Or sometimes I'll just, without putting that arc in there, call it angle A. These mean angle A. The same for the measure of angle A. Another way that we can do that to differentiate different angles is you can put a little slash in the arc. What that means when I do that is that these 2 angles are the same. If I have yet another angle, I could put 2 slashes in. Well, this angle is not equal to that angle because this has 2 marks in it. This has 1. So this angle and this angle would be the same by putting 2 marks there in the angle. Now, another way that it's done is if we have, say, 2 angles and I want to say differentiate it from this angle, we could put several arcs there. But that gets a little messy if you have, say, more than 3. If you have 3 different angles, then you'd be doing that, and it gets rather messy. It's better to use the tick marks when you have trying to designate more than 3 angles, 3 types of angles. But I'll use those interchangeably. Say, suppose you have 2 triangles. We have a triangle here, and we have a similar, say, a congruent triangle sitting here. Well, we can show that they're congruent, or at least similar, by saying, all right, I've got this angle. That is going to be the same as this angle. This angle is the same as that angle. This angle here is the same as that angle there. And that's how we designate similarity between figures in geometry. Now, if 2 angles are equal in measure, we also call them congruent. That is, angle A is congruent to angle B if they're equal in measure. Or I will a lot of times just say angle A is equal to angle B, meaning that they're also congruent. That congruency means that they have equal measures. So both of these ways are acceptable to express that. And say, if I want to say angle A is equal to angle B is equal to angle C, that tells me that all three angles have the same measure. That is, that they're congruent. Remember that angles that have the same measure are called congruent. Congruent angles do not have to point in the same direction. For example, I could have this angle of 60 degrees. I could have this angle, say, of 60 degrees. These two angles are congruent. It doesn't matter how these angles are oriented. Now, consider two parallel lines. If we have two parallel lines and we intersect it with a line that isn't orthogonal. Orthogonal means at right angles. We take a general line and intersect two parallel lines. This is called the transversal. The line that intersects two parallel lines is called a transversal. Now, there are 8 angles that are defined when we intersect two parallel lines with a transversal. This is angle 1. Let's call this angle 2. This is angle 3. This is angle 4. We'll call this angle 5, angle 6, angle 7, and angle 8. There are 8 angles that are defined. And these various combinations of pairs of angles have special names to them. We call corresponding angles the corresponding angles are those angles that lie in the same corner of the intersections. That is, angles 1 and 5 are corresponding angles. See, they lie in the same type of corner in relation to their respective vertexes. 1 and 5 are corresponding angles. 2 and 6 will be corresponding angles. Another set of corresponding angles would be 4 and 8. This corner is the same as that corner, and 3 and 7 will be corresponding angles. So we have 3 and 7 and 4 and 8. So those are our angle pairs that are called corresponding. That's 2 R's in there. Called corresponding angles. Now, by definition, all corresponding angles are congruent, that they have the same measure. They appear in the same corner, the same type of corner. So corresponding angles are congruent, or they're the same measure. Now, angles that lie between the two parallel lines, between them, are called the interior angles. So, the interior angles will be 3, 4, 5, and 6. The exterior angles, as you might guess, are the angles outside of the two parallel lines. In this case, it's 1, 2, 7, and 8. Now, a similar sort of thing happens like with a triangle. If we have angle A, angle B, angle C, and say we have here angle 1, and let's call this angle here angle 2. A, B, and C are the interior angles to the triangle, whereas 1 and 2 are exterior to the triangle. Interior angles are contained within the area of the triangle, and anything outside of the area of the triangle is called exterior angles. Now, we have what are called transverse angles, and they are related to the transversal. That is, the transverse angles are 4 and 8. They're on the same side of the transverse. We have 2 and 6, 1 and 5, 3 and 7. So the transverse angles are 4 and 8, 2 and 6, 1 and 5, 3 and 7. These are angle pairs. When we talk about transverse angles or corresponding angles, we're talking about pairs of angles. So 4 and 8, 2 and 6, 3 and 7, 1 and 5 are transverse angles. These are angles that have the same corners on the same side of the transversal. So we call those transverse angles. Now, a vertical angle pair are angles 2 and 3, 1 and 4, 6 and 7, 5 and 8. They're on opposite sides of the vertex. So vertical angles are the angle pairs 2, 3, 1, 4, 5, 8, and 6, 7, or 7, 6. These are called vertical angles. Now, vertical angles are congruent. They're equal to one another. And we can easily see that is, suppose, let's just take two lines that are crossing. The contention is that angle A and angle B, which lies on opposite sides of the vertex, are equal in measure. Well, suppose we call this angle here C. That's going between these two rays or sides. Then we know A plus C is 180 degrees by the definition of supplementary angles. A plus C sum to a straight angle. So A plus C is 180 degrees. Also, C plus B is 180 degrees. So B plus C equals 180 degrees. Now, we can equate them. Since A plus C is 180, B plus C is 180. A plus C is equal to B plus C. Well, we can eliminate the C on both sides. It's not affecting the overall equality here. So from this we conclude that A equals B. We can cancel out the C on both sides. So we get A is equal to B. So vertical angles are congruent. They're equal in measure. We now have a few more definitions of angles to go through. I've rewritten everything here. These are the ones that we've defined so far up through the vertical angles. Now we'll talk about the consecutive interior angles. Well, the interior angles are 3, 4, 5, and 6. So alternate interior angles must be involving these in some way, pairs of these angles. Well, the consecutive interior. Consecutive interior are the pairs 4, 6, and 3, 5. So 3, 4, consecutive, that or 4, 6, the consecutive, these are interior angles, so they're consecutive on the same side of the transversal, and 3, 5 are the consecutive interior angles on the other side of the transversal. The alternate interiors are 3, 6, and 4, 5. 3, 6 are alternate. They're on the other sides. They're alternate sides of the transversal. So 3, 6, 4, 5. So the interior angles, consecutive, interior, alternate interior, have to do with the angles on the interior between the two lines and having to go across the transversal if we're on the alternate, and on the same side of the transversal if it's consecutive interior. Now the alternate exterior angles, since the exterior angles are 1, 2, 7, and 8, and we're doing an alternate like we did with the interior, you would guess that the alternate exteriors would be 1, 8, 2, and 7. And that's what they are. So it's a pair 1, 8, 2, 7.